Okay, we're going to do a little mini lecture here to consider some of the applications of the Euler equation when we're interested in thinking about specifically rigid body accelerations. So the Euler equation tells us that pressure gradients and body forces can lead to accelerations, as I've summarized here in this equation. So here are the forces that are acting on a material element. And if we're dealing with a rigid body, then we can write the acceleration as just the density per unit volume of the material multiplied by its acceleration. And to remind us, this is really what we mean is the time rate of change of velocity following a material element. We can rearrange this equation, so I can write it the following way, and this tells me now that gradients in pressure fields are balanced by this net acceleration vector, which is the vector sum of G and A. So the first thing we can see we might take away from this is that pressure gradients act along a line of this vector. So if I have a vector G minus A that looks like this, then pressure gradients are acting in this direction. And so as we know, we'll know that pressure gradients certainly can drive flows or drive accelerations. And so we might be interested in understanding what direction this net vector G minus A is. The other thing that we can take away from this is that we can draw isobars. An isobar is a line of constant pressure. So iso is the Greek word for equal, and so this means equal pressures. And so here are a set of isobars that I've drawn. And the important thing to recognize is that they are orthogonal to G minus A. So this angle is 90 degrees. How can I see that? Well, I can see that quite easily because I can trying to think about constructing something that was the combination of a line along a line of constant pressure and G minus A. And I could think about taking what I might think about as the curl of G minus A. And the curl of G minus A is nothing but the curl of, since we know that that's the same as the gradient of pressure, as the curl of grad P. And so anytime that I take the curl of the gradient of a scalar, the net result is always zero. And so that certainly tells us that therefore that these lines of constant pressure are orthogonal to this vector G minus A. So that's a very useful insight when we're looking at pressure fields. There's a couple of simple ways that we can think about applying this equation. And so we're going to think about different ways of applying this equation now. The first and simplest one is to think about free fall, or what happens in an object undergoing free fall. For reference, let's first of all think about an object, let's say a glass of water. So we've got some liquid in a glass. And it's not under acceleration. So it's first of all, consider this system at rest. You might say that the acceleration is zero. And then we know from hydrostatics then that if we take our Euler equation, if acceleration is equal to zero, then we're just going to balance these terms. And so we'll end up getting that if this is zero, that we'll have grad P is equal to rho G. And so the expression for the pressure variation in this beaker of water, we've already worked out before. The pressure's highest at the bottom, and the pressure at the bottom, P1, we might find would be given by the atmospheric pressure at the surface plus rho GH, where this is PA. And the sign, of course, we have to be very careful to recognize that if we're going to define Z as being upwards in this direction, then our gravity vector here, G, is equal to minus G EZ. And that allows us to get the sign right. However, if I drop this glass of water and it accelerates under gravity, so if I instead accelerate this and say that the acceleration is equal to gravity, so now this glass of water falls and its acceleration A is equal to G, and is pointing in the minus Z direction, then now we have, when we think about our force balance, we have that the gradient of pressure is equal to rho times G minus the acceleration, and the acceleration is equal to G. And so that says that the gradient in pressure is equal to zero. Or in other words, the pressure is a constant everywhere. So now in this case, if the pressure is atmospheric here, the pressure is also atmospheric here. And anyone who's ever experienced that kind of drop in that strange feeling in your stomach when an elevator initially drops, that's exactly what you're feeling, is your stomach is suddenly experiencing that the contents are all at exactly the same pressure, and there's no load keeping the contents of your stomach at the bottom of your stomach. And the most common application, of course, of this is in microgravity. And so this allows us to image liquids. And so in microgravity, for example, on the International Space Station, the acceleration is very, very close to gravitational acceleration. And so there is no tendency for a liquid to want to stay in a container. In fact, if I take a blob of liquid and I take it out of the container, its pressure is the same everywhere. So the pressure is constant everywhere. But the boundary condition that becomes important is the action of surface tension. So surface tension acts at the boundary. And so it will take a blob of material, and surface tension will try and minimize the surface area available. And so it will turn our contents into essentially a liquid drop of a fixed radius, where the volume here is the same as the volume here. And of course, there are many great examples of this that you can find on YouTube through NASA TV. Here's a great example of a NASA astronaut who's died a drop of liquid green. And you can see that indeed there's no hydrostatic variation. The pressure is essentially constant everywhere. And surface tension is making this into a sphere. Okay, so that's the simplest example. Slightly more complicated example is to think about a linear acceleration. So a linear acceleration, we might think about, say, for example, our glass of water again, but now I'm going to think about accelerating the glass. And so in this case that I've drawn here, the glass is accelerating in this direction, and I'll write it as a times EX, where I've defined my coordinate system so that, again, gravity is minus g EZ, pointing downwards, and my coordinate system is as drawn. So when a glass accelerates like this, what you'll actually find is that the free surface arranges itself so that it's inclined like this, and we might like to understand what the angle of that inclination is. So all we have to do is think about this idea that the gradient in the pressure is equal to G minus A, again, with a scalar rho in front of it. Now we recognize that this is a vector, so we might need to write out all three components of it. So we might like to introduce dP by dy and dP by dz. And so we know that we can write out all of these different components. And so in this case, we'll have minus A in the x direction, we'll have 0 in the y direction, and we'll have minus g in the z direction. As I recognize that we've got a minus sign here, so that gives me this. And g is given by minus g Ez. So this gives me a set of differential equations that I can solve. And so I can actually solve this. And so I can find an expression for the variation in the pressure field. And the simplest way of realizing this is to recognize that what we might typically see is we might typically see, again, a line of constant pressure. So we might like to think about what the equation of an isobar is. So an isobar is a line, as we've mentioned, where the pressure is constant. And so the simplest one might be the line where the pressure is constant at the free surface. But we can write this more generally as by saying that dP by ds, so along a free surface, which I'll indicate by s, dP by ds is equal to partial dP by dx times dxs plus partial dP by dz times zs, where I'm being very explicit to indicate that when I'm moving along a surface, I'm thinking about taking a step dx and a step dz along the surface. So if I combine this with the statement that we've got here, the variation of pressure along a surface is 0 because it's a constant pressure surface. So dp is 0. And now I can substitute for dp by dx is minus rho a times dxs and minus rho g dzs. And so I can easily see, if I like to rearrange this, I can write this as the angle of my surface, which would be equal to d zs by dxs is equal to, and so just by rearranging this, I'll get that it's equal to minus a over g. And so as I've drawn it here, this angle theta is negative. A is a positive scalar. So as I've written here, A is a positive scalar. G is a positive scalar. So the angle of my surface is negative. And so sure enough, the surface slopes down like this. Another way of thinking about this, and a good exercise, is to ask where is the pressure highest in this material? And we know that the gradient of pressure is aligned in this direction. So the gradient of the pressure is aligned in this direction because that's the combination of this vector and this vector. And then it's clear that the gravitational component is negative. So in fact, the direction of increasing pressure is in this direction. And this is minus the gradient in pressure. So the pressure increases in this direction. And in fact, the largest pressure is in this bottom corner here. And the liquid piles up here so that the largest pressure there is exactly balanced by the weight of the material that's above it. Similarly, over in this corner, there's less material. And so the pressure here is lower than that. And there's a pressure gradient in the x direction, which is exactly given by these terms right here. And so the pressure is lower here than it is here, or in other words, dp by dx is minus a. So a good exercise, if you want to just think this through, is to consider the case of deceleration now. So now the acceleration is negative. And so we might write that the acceleration is minus a times ex. And you should work this through. And now you'll see that when you decelerate, the liquid piles up at the front of the glass. And so the acceleration is a deceleration in this direction, or rather an acceleration in this direction. And you'll find that the liquid piles up at the front of the glass. And so now the highest pressure is down in the bottom corner here. And the gradient in pressure is aligned in this direction. So next time you decelerate heavily in a car and you've got a glass of hot coffee between your legs, you'll recognize that when you decelerate, eventually what will happen is if you decelerate too fast, then the angle will increase. You'll find an expression for tan theta, which will be positive. And if you decelerate too fast, then your coffee is going to come out all over your lap.